Let's see. Our next speaker is Kevin Menard. He works for Oracle, which they make a database that I have used before. Maybe some of you have used it before too. He is going to talk to us about a tale of two string representations, and I think that this will be a very interesting tale. So everybody, please welcome Kevin.
All right, hi everybody. So my name's Kevin. I'm a principal member of technical staff at Oracle Labs, where I work on JRuby+Truffle. For those of you that aren't familiar with it, it's a new implementation of Ruby using the Truffle self-optimizing AST interpreter, which is used in conjunction with the Graal virtual machine or compiler. Realize it's a mouthful, but basically we're trying to build a new high-speed implementation of Ruby, and we ship with JRuby as an alternative backend. Before I get started, I do need to inform you that what I'm presenting today is research work out of a research group. It's not a product announcement, and you should not buy or sell stock in Oracle based on anything you hear today. All right, with that out of the way, let's tell a tale of two string representations. Fittingly enough, it makes sense to start our tale with the string. And now we can move into representations. So the first representation here is rstring, which is basically the way MRI internally represents strings. And really, it's the way all the Ruby implementations implement strings. JRuby uses a very direct port of MRI C code to Java. Rubinius, I believe, just takes the MRI code entirely. And our strings are structured very similarly to how strings in C are structured. So what we have is a byte array, and then we have a length field, so we can know how far to look into that byte array. And then we have an encoding. So Ruby strings are encoding aware. And we associate encoding with the string, so we know how to interpret the byte sequence. And then there's this code range field, which is used as something of a cache of information we know about the underlying byte array, given the current encoding. And there are some additional fields here that I'm not representing. This is mostly just for simplification. I do have a reference slide later on that lets you see all the gory details of rstring if you're interested. But the key features of rstrings are they're a mutable flat representation. So when we want to represent a string, we need to be able to allocate a contiguous region of memory to represent the contents. And then operations with rstrings are essentially byte-oriented. Nearly everything we want to do requires reading from that byte array or directly manipulating it. Now, Ruby strings are mutable, and rstrings are mutable. But in practice, many Ruby strings are effectively immutable. Throughout their life cycle, they never actually change. And it would be a shame if we had to waste all these bytes trying to represent the contents of two identical strings that never change. So rstring has a mechanism for sharing the underlying byte array using copy on write. Our second representation are ropes. So ropes are an immutable tree structure. And what we have is at the leaves, we have these string fragments. And underneath the covers, they're very similar to rstrings. We still have a byte array. We still have an encoding. We still have a code range. We can't get away from those facts. But the leaves are immutable. The byte array can never change. It can never grow or shrink, and its contents can never change. So if we want to manipulate a rope, what we need to do is build on top of it. So we have a persistent data structure, and we build on top of it by using these operation labeled nodes. So ropes are immutable, and they're a tree representation. An interesting side effect of this is we don't need contiguous memory to allocate them. So if you wanted to allocate a 1 gigabyte string with rstrings, you would need to have that available in your heap. With ropes, you can do this by having multiple different leaves, each allocated individually. So it's almost a difference between like an array and a linked list. You might be wondering why you'd ever want to do that. Well, strings in Ruby are used for more than just sequences of characters. They're also used as a general byte buffer data type. So if you're dealing with binary data or working with I/O operations, you may very well need to allocate a large string. But by having this tree structure and having each of the leaves immutable, it shapes the way that we think about operations. Instead of always looking at the underlying byte array, we think more in terms of logical string fragments. And because each of the levels at the tree are immutable, we trivially reuse memory by allowing nodes to appear in multiple trees. So ropes are kind of an older idea. They were originally proposed as an alternative to strings in this environment called Cedar. But with Ruby, we already have a string type. We don't want to introduce another new type. We want to work with code that's already out there. So our idea was to change the representation for strings with ropes. But ropes needed to be modernized for Ruby. So ropes, as they were originally proposed, modeled C strings very closely. They were byte-oriented. They weren't aware of encodings. All of the methods called on them were done through library functions. So with our ropes, we've updated them so we have operations that correspond to Ruby semantics, and each of the leaves is encoding aware. So these values you see down here roughly match the code range information. All right, so we have our two representations. We can kind of see that they're laid out differently in memory. But what does this practically mean operation-wise? So I'm going to run through some operations here. The first is string concatenation. I do apologize for the slightly confusing terminology. I'm using the terms as they appear in the string RDoc, which has concatenation as the immutable version with the plus operator, and append as the mutable version with the stream in operator. But I have code samples for all this, so hopefully you can follow along. But basically, we have x and y. We want to concatenate them and get a new copy z. So we have on the right is the byte array for x and the byte array for y. So the first thing we need to do is allocate a new buffer large enough to hold both our contents. So this buffer is as big as x and y. Then we copy over x. Then we copy over y. And we're done. So this is a linear time operation. We had to do a single memory allocation, one large enough to hold both the contents of x and y, then two memory copies. And at the end of this process, we have two copies of x and y in memory, because x and y still exist as variables themselves, but their contents now appear in z. In contrast, this is how concatenation would look like with ropes. So we have our ASCII-only leaf ropes. So these are the encoding-aware leaves I mentioned previously. And these do have their byte arrays. But when we want to concatenate them, we just allocate a concat rope node and point it to the two leaves. So this is a constant time operation. And while we needed to allocate memory for that node, we didn't need to allocate a new buffer, and we didn't need to copy any memory. And at the end of this process, we still only have a single copy of x and y in memory. So I ran a benchmark that was intended to emulate what one would do with ERB. So this did a tight loop of concatenations of HTML fragments. And then at the end of the process, wrote the bytes out to dev null to simulate a web server response. And the way to kind of understand this graph is all values are relative to MRI, which appears on the left. So MRI is as fast as itself, so it's a 1.0x. JRuby is about 20% faster on this. And then I ran the numbers two ways with JRuby+Truffle, one using an R-string implementation and one using ropes. And the reason to do both is each of these language implementations has a different underlying runtime, a different compiler. So I didn't want to attribute things to ropes that could be easily attributed to the differences in just the compilers. But what we can see here is ropes vastly outperform the others. So then I reran the same benchmark using string append. This is the mutable version. And what we can see is the numbers collapse. This is because the other implementations get a lot faster. So here, JRuby is about twice as fast as MRI. Now keep in mind, they're running almost identical code. So this speed up is basically due to having an optimizing compiler in play. Then we have the JRuby+Truffle R string, which is about 3 times as fast as MRI. And then we have our ropes, which are about twice as fast. So in this situation, ropes are a little bit slower than R strings, at least as they're implemented in Truffle. This can be attributed to Truffle's object model, which is optimized for reads rather than writes. So ropes are immutable. On each of these append operations, we still need to allocate a new node, and we need to update the reference to that rope in the corresponding Ruby object, and those updates can be kind of slow. I believe this is something we can fix in Truffle, but as we can see, it's a little bit of improvement for ropes, but we're still faster than R strings with other implementations. But I think what's really interesting to do is compare how the different implementations do concatenation versus append. And there's a big gap here. So for this particular benchmark, using string append is about 40 times faster in MRI, about 65 times faster in JRuby, 138 times faster with R strings and Truffle. And then when we get to ropes, the performance difference is negligible. And I think this is important. We shouldn't have these wide performance gaps, I guess. They create issues for you in production because on small enough data, you might not actually see it, but when you get into larger streams of data, all of a sudden the choice of using the plus operator rather than the stream in one presents itself as a performance issue for you and one that you wouldn't have anticipated. But the other reason I really think this is problematic is the notion of mutability for an object is behavioral. You shouldn't pick a mutable or immutable version of something simply for performance. Because mutability tells something about your code, what you intended. Likewise, as Rubyists, we like to write code that looks nice. And for a lot of people, using that plus operator to add 2 strings together is a natural thing to do. And we shouldn't penalize people for doing this. So with ropes, with string append, we see a slight dip on performance over R strings, but I think it's made up by the fact that you can choose either version of concatenation and get roughly equal performance. So if we want to abstract the notion of concatenation, these are the set of string methods that can be implemented using ropes. So now I'm just going to go through some other operations. We have substring with R strings. So we have our hello string. We want to get the middle 3 bytes. We can see the byte array. First thing we do is allocate a new output buffer, copy the data. We're done. With ropes, again, we don't need to do a buffer allocation. We don't need to do a memory copy. We just create a new substring rope, set some metadata fields to indicate the offset and the byte length, and we're done. So here's the set of operations that can be represented using substrings. So there's kind of a prevailing theme here where we can generalize the action for a lot of these different methods. And if we can make those generalized actions fast, we can have wide-reaching consequences. Another one here is the multiplication operator. So here we want to triplicate, I guess, the string x. So what we do is we allocate a new buffer for 9 bytes. We do a copy, and a copy. With ropes, we can just have a repeating rope node. So in this case, we just allocate the repeating rope node, indicate that it's multiplied 3 times, and point to the original rope. So these are all lazy operations. We don't need to materialize the underlying byte array until we actually need it. And this is why the concatenation operation was so much faster for ropes. If you're doing 10,000 concatenations and you only need the bytes at the end, all those intermediary buffer allocations you're doing are unnecessary. So by deferring the operation, we're able to limit the memory allocation until we actually need it. And in using ropes, we might not even need to allocate it at all. So for instance, with a repeating rope, if you want the 4th character, we can take that times value in the underlying byte length and just offset into the child without materializing the array at all. All right, so let's take a step back again. So we have our hello string, and we can query it. Ruby has a very rich string API. So here we can see that hello is made up of 5 bytes. We can also see that it's made up of 5 characters. So in this case, the hello string is UTF-8 encoded, and UTF-8 is ASCII compatible. So hello here is made up of only ASCII characters, and in ASCII, each character can be represented by a single byte. So the number of bytes and the number of characters line up. And this is nice. We can do some nice optimizations in Ruby based on that. So I ran a little benchmark here where I took the size of the hello string, and then I multiplied hello 100 times and took its size. And we can see as the performance is essentially the same. This is a constant time operation. Our strings already have that byte length field, and they can just return it. And ropes have something very similar. So what we can see is JRuby, again, is about twice as fast as MRI. And in these particular benchmarks, Truffle is about 17 times faster. And this is because truffles can optimize very well in conjunction with Graal, a lot of constant folding and things like that. But here's another string. I took this from Ruby spec. I assume it means something like ignorant American. I don't really know. But what I do know is it's made up of 12 bytes, but only 4 characters. So now we have our first mismatch. And the thing to note about UTF-8 is that it's a variable width encoding. So you might be tempted to think, all right, well, we can take the 12 bytes, divide it by 3, and say each character is 3 bytes wide and get the count at 4. But that's not how UTF-8 works. A character can be anywhere between 1 and 6 bytes. So now when we do that same kind of string length calculation, we see a much bigger gap here. So I took the string, took its size, multiplied it by 100, and also took its size. And we can see another benefit of ropes here. So because ropes are immutable, we're able to cache the character length inside the rope itself. So this benchmark's a bit unfair because for ropes, it's a constant time operation, where with our strings, we have to do a full byte scan if we want to get that character length. And again, I wanted to see what the relative difference was on each of the implementations. So taking these strings, and I did the 100 multiplied time case, we can see MRI is about 4 times faster on ASCII-only data versus non-ASCII data. JRuby is about 7 or 8 times faster. And then with ropes, we have no performance difference whatsoever. So I think this, again, is important. We shouldn't have hidden performance pitfalls. So where this might come up is if you're doing a web application and you've written your templates all in ASCII, but you allow user-supplied data, maybe their name, their address, company name, what have you, and it has a non-ASCII character in it, the performance profile for your application can change drastically. Suddenly, things that were constant time are now linear time. And if you're just taking the mean of your performance values, you're not really even going to notice that there's a problem here because you have a bimodal distribution, and it gets washed over by just taking the mean. Now, you might be thinking, well, who cares about string length? How often do I do that? String length actually is invoked repeatedly within the core implementation. Anytime you want to get something by index, you need to know the string length so you can do bounds checking. So if you want to get a character at position -1, you need to know that that's really the last character and work your way through. So there's no reason we couldn't do this with our strings, but it gets a lot more difficult because that underlying byte array can be invalidated at any point, and when it's invalidated, you need to be able to update the character length efficiently. Whereas with ropes, we're able to basically propagate the value up. So for the leaves, we may need to do a full linear scan, but once we do it, we never have to do it again. But if we take, say, that repeating rope example, if we know the character length is 4 and we're multiplying it by 100, then we can just say the character length is 400. Whereas if you did this with our strings, you'd end up with a completely new memory buffer 400 bytes, and you'd have to do a full scan through it. All right, so I just want to wrap up a bit here. So there are other benefits to ropes. There's a lot of operations that we've modeled in JRuby+Truffle. Basically have, we replaced R strings throughout the entire implementation, except in these places where we allow switching it back and forth. But we default to using ropes now. And what it's allowed us to do is reduce memory consumption generally, because when we have different strings that basically are logically equivalent, we can intern those, basically meaning we can use the same rope repeatedly throughout. And this is really important for metaprogramming. So last year I gave a talk on metaprogramming and mentioned that we use a cache on the method name or a variable name in order to do fast lookups. But this is problematic if you can't have referential equality. So we want to be able to say a method name and a string supplied by user code basically are the exact same rope. And if we can do a reference check, we can do that basically very quickly with simple integer comparisons. But if we don't know that they're equal like that, we need to do a linear scan and do byte-wise comparisons between both. And while that works, having this guard take so long basically eliminates any value you would have gained by caching it. And by having immutable values, this is really nice for optimizing compilers, especially things like Graal, which uses partial evaluation to do aggressive inlining and constant folding. Having constant values really aids that process. And a recurring theme throughout this conference has been concurrency. Ropes are implicitly thread safe. So while we still have a reference from our Ruby string to a rope, and you could have two threads race on that, you'll never see mysterious byte updates because the byte array for each of the levels in a rope can't change. Now, there are some deficiencies. So I mentioned previously that Ruby strings basically have dual functions. One is it has a sequence of characters, which is essentially how I've been talking about ropes. But they can also be used as a byte buffer. And in this case, ropes aren't really a great fit, particularly if you have a stream of binary data and you need to call set byte, so you're updating a single byte at a time. These rope nodes end up dominating the cost of the piece of data it wants to update. So if the node is 16, 32, or 64 bytes, but you only want to update a single byte, your node overhead complicates things. So I think we can come up with better ways of doing that, but it's future work. And then, excuse me. So I like ropes because I think they make some key operations in Ruby much faster, but if you have experience doing performance work at all in Ruby, and particularly if you've come from a C background where you're accustomed to think about the asymptotic complexity of operations in a certain way, by completely changing that equation, we make things a little bit harder. So I think this is something that can be overcome just by having more experience with it. But for instance, if you want to fetch a character out of an R string, and the R string consists of only ASCII data, we can do that in constant time. But with ropes, we need to traverse the tree, so there's a logarithmic time added to this. And if you get in a situation where the rope is very badly balanced, it could degrade to linear time. Having said that, the rope performance is much more normalized across the various encodings. If you take that same R string and add non-ASCII data into it, and you want to fetch a character, now you're back to linear time. So I think part of what we need to do is try to smooth over these differences between encodings so you can think more reasonably about how your strings are going to perform. So these are some quick references. I do just want to point out that Pat Shaughnessy, who wrote Ruby Under a Microscope, has a great set of blog posts that investigate R strings and some of the performance characteristics of them. And under ropes, There was actually a Google Summer of Code project for MRI to add ropes I just learned about recently. So the student wrote a very nice write-up there about applying ropes to a different Ruby implementation. And all the benchmark code I used here is publicly available. So to recap, ropes are an alternative way to represent strings. I think they present an interesting bridge between Ruby strings, which are mutable, and the way they're actually used, which is most of the time Ruby strings are immutable. And ropes being an immutable data type kind of take advantage of the fact that Ruby strings frequently are not ever changed. So far, this experiment has been working out quite well with JRuby+Truffle and Graal. I believe it would actually work out quite well for other implementations as well. The fact that fields are final works very nicely for our compiler, but I think it could bring benefits to both MRI and JRuby. And then just as language implementers, I think we need to make these core operations fast and compact. And when we have something that's been kind of in place for a long time, it's easy to think that that's basically the only way to implement something. And then we profile it, and we find we can make things marginally faster, but we're stuck in a local maximum. So ropes are, I don't want to say novel, because the idea has been around for 30 years, but it's a new approach for us for representing string data, and something I think that as language implementers we should look at for other core data types as well. And just want to thank a bunch of people. So I didn't do all this work myself. The folks up on the left in bold are either on the JRuby+Truffle team or their Ruby implementations we've taken code from. And that's about it. Here's my contact information. Please feel free to email me or tweet me or reach out on GitHub if you have any questions about this. I love talking about this stuff. And that's about it. Thank you for your time.
I believe we have time for questions, so any questions? Yes. Uh-oh. Good luck, Kevin.
I'm mentor of Google Summer of Code rope project. So he make a rope structure on MRI, and so the result is maybe similar one. But our approach, so I have two questions. So one question, the first question is, so for the practical applications, so most of people use so concatenation, so instead of plus. So there are no so huge improvement on the such practical applications. So what do you think about that?
So the benchmark I used was actually extracted from ERB, and ERB was using plus. So if that's no longer the case, I guess I need to update it. But I tried to pick something that was representative of how people would write code.
Okay.
And I did a kind of soft survey of code on GitHub, and there seems to be plenty of Ruby code out there that does use the plus operator. Perhaps it's not performance critical, but.
Okay, so another one is such a the technique introduce many complication. So it means that the source code is very huge using the rope structure. So string class, the C source code is increased 2,000 lines. So this is why we hesitate to introduce rope instruction. So what do you think of the complication? And so complication is disadvantage, and advantage is performance. So what do you think of such a trade-off?
Sorry, so I didn't quite get that. The complication was the code got a lot larger?
Yes, and so it's difficult to read and difficult to understand and difficult to debug or something. So maybe the simple string is very easy to understand, so straightforward buffer, but rope is some complex structure. So so and also such a complexity introduce some overhead. So you say in for other methods. So what do you think? So
yeah.
there are,
So
okay, please.
obviously, a fair bit of this is subjective. So for us, what I found interesting about ropes is we can model a lot of operations using a core set of nodes. So taking a substring of string, getting a character out of it using slice. There's multiple operations that we can model just using substring node. And by doing that, I think we're able to kind of surface this commonality and find ways to more efficiently represent them. I do agree that when you're looking at the underlying representation, it can get much larger because now you have a tree, and if you want to print a tree out to the console, that's a little difficult. On the other hand, I've kind of found that helpful too because the tree ends up functioning almost like a call profile. So if you see a ton of concat nodes back to back to back, it suggests that maybe you're not doing something quite efficiently with your string. So our string, you wouldn't have all these concat nodes, obviously, but even when you're using string append, the mutable version, you could very well be constantly reallocating buffers. You're not creating new R strings, but that underlying buffer, if it doesn't have spare capacity, needs to be rewritten. And I think having a long tree kind of makes it obvious that maybe you could be doing something perhaps a bit more efficiently. But I think a lot of this is also just familiarity. So we're not kind of accustomed to think in terms of trees for string representations. So when you see them, it looks foreign, and you might not know how to deal with it at first. I think as we get more accustomed to looking at it, it becomes less scary, I guess. I don't know, did that answer your question?
Maybe I can't understand everything, so please discuss later.
I'm sorry, what was that?
Let's discuss later.
Okay, yeah, sure. I'm not trying to misrepresent anything.
Any other questions? Oh, here we go. Yes.
So in JRuby+Truffle, everything is now ropes, right?
Yes.
But then in MRI, in what I understand in the current patch, it's a mix of like essentially buffer string and ropes. So do you think it would be interesting to preserve both? So for instance, to have concats be the most efficient with a buffer, or do you think with the given performance number that a rope is just good enough to represent all operations?
In the case of using a string as a sequence of characters, I think having ropes is generally good enough for us. There are certainly daemon cases that probably require some more investigation. So in particular, if you have a string and all you want to append is like a new line, now you've allocated this concat rope node, which might be 32 bytes, and you're really looking at CRLF or CRLF, so 1 or 2 bytes, and now the node dominates the cost of the thing you want to do. So traditionally with ropes, as written in the paper, for these very small concatenations, they'll actually combine them. So as you append 1 or 2 bytes multiple times in a row, rather than keep allocating new concat rope nodes, it'll flatten them implicitly. We currently don't do that. I think it's something we could be looking into a bit more. We had done it initially, and what happened was because we compiled all this code, we ended up having very large methods, and that complicated performance as well. So I backed that out as something to look at further down the road.
Okay, thanks.
I have questions. Is that okay? Can I ask questions?
By all means.
Okay, do multiple string instances share pointers to ropes?
Yes.
Do you ever get into a situation where maybe you have to copy an entire subsection of a tree? Like, for example, you have two string instances, and they both point at the same rope, but maybe one points in the middle of it, or some other node, some child node, do you ever get into a situation where you have to copy that subtree to the other one? Does that make sense? Like essentially copy on write operations?
I'm not sure I follow, but if you want to get into the middle of it, you would use that substring rope and then just set the offset. So you wouldn't actually need to copy the underlying data.
Okay, but if that one string gets mutated, okay, maybe I'll ask you
Yeah,
about this
it can't
later.
get mutated, so the underlying string can belong to multiple trees.
Okay,
So if, I don't know, take the string ABC, if one case you want to append DEF, that string can belong to a concat rope. But if you also want to get just BC out of it, that same leaf can belong to a substring rope.
okay.
That makes sense.
Yeah, that makes sense. Okay. I have one more question. So the rope implementation is much more complex than the previous buffered implementation. Is that true?
I think it's actually clearer.
It's more clear?
Yeah, I don't know if you've looked at the string code in any detail, but it is not easy to wrap your head around.
Okay.
Part of the reason I think it got clearer, and I'm sorry if no one's really looked at this, but with our strings, because the character length is not cached or pre-calculated, and because the code range also isn't pre-calculated, basically every operation that would involve one of the two needs to do it in place. Whereas because our ropes are immutable, we actually calculate both the character length and the code range up front, and then they never change. So this notion of an unknown code range simply doesn't exist. And then we can, because we know it in advance, we have specialized operations in Truffle, so our code paths get a lot clearer. If you know you're concatenating two ASCII 7-bit strings, we can represent that separately from doing it with non-ASCII strings, for instance. Yeah.
Oh, we have another question? Huh? No? No? Yes? Come up.
Yeah. Okay, my question is, if a string got a lot of operations, and a tree will grow up, right?
Yes.
So if we want to have a long-running process, we want to let it run like for a year, and the process, a tree will become enormous. Is there any way to like flatten the tree?
Yeah. So again, I have in that reference slide the original rope implementation. They have this weird flattening algorithm based on the Fibonacci sequence. But you could do it much more simply by just depth limiting. So on any operation that would grow the tree, you could say, okay, if we've now exceeded depth of 100, we'll just flatten one of these subtrees and then we'll concatenate them together. We're currently not doing that, but it's a trivial extension, I guess.
Okay, I think our time's about up. I have one more question though. The rope code that you wrote, is it isolated from the rest of the string code? Are you implementing buffers and ropes at the same time? I think you said.
Yeah. So this is a bit messy. So we're doing it in Java, and it doesn't have multiple inheritance. So I have this notion of a rope buffer, which is actually a rope that has mutable bytes. So that rope buffer can only have a single reference. Otherwise, everything falls apart. But
it's
otherwise, we can just map it into other calls.
It's pretty well isolated though, right?
Yes. Yeah.
So you could definitely say it's roped off.
Oh boy, I should have saw that coming.
Thank you, Kevin. That is all.